All right, now let's do another common sense idea here. I'm going to do it on this side. If I have any type of triangle again, how many angles do I have? I have A, B, and C, right? How many angle bisectors should I have then? Oh yeah, I should have 3. I should be able to go and draw these in. You do not have to draw this, my friends. And there, you know, look what happens to the angle bisectors. They also intersected at a point. And so they also have a point of concurrency. That point of concurrency is called the in-center of the triangle. So that point right here is called the in-center. So it's another terminology that we use. Now, in-center, but think about the angles, if you bisect them, are always going to be in the middle. So what they're telling us here in this diagram is the in-center of a triangle is equidistant from the sides of the triangle. So it's equidistant from the sides of the triangle. What do we mean? That means if I draw in where all my angle bisectors intersect, that's point P, okay? Point P is the in-center. Then I can automatically assume that these 3 smaller segments are all the same size. And then we can prove it using congruent triangles and stuff like that. We're not going to worry about that right now, but that's what we're coming up with as our reason. Now, and they said, you want you to remember, why does that work? This is all the same distance away from a segment, but that is what we learned the other day. But let's draw the in-center on every one of these triangles for an acute, obtuse, and right triangle. All right? Now, the in-center, this time though, is always inside the triangle. Because notice, if I do an angle bisector, it doesn't have to bisect the sides. Just remember that. So I'm looking at each angle and just dividing it. Oops, that one was really bad. Try to get a little bit better here. Let's say those work. Those get 3 marks. Notice where it hits on the inside. Look, even an obtuse triangle. If I go and I bisect, try as much as I possibly can here. Here we go, that angle. I'm going to bisect this one right here. 1, 2, 1, 2 marks. If I do the angle bisector again, so they're all the same size, they're all intersecting in the middle. So there is going to be my in-center every time. Even a right triangle, this one's easier to get. Here's my right triangle, so I'm going to bisect that angle. Notice it doesn't go through the midpoint in this case. So I get 2 congruent 45-degree angles. And then I have my other 2. I have this angle being bisected. I'll have this angle being bisected. And right there, every one of those, I'm going to do them in red here, is the in-center. Notice they're all on the inside. The in-center is inside. It's formed by the angle bisectors. Now, here's kind of the cool thing here. The in-center of, how did it got his name, is the center of the triangle's inscribed circle. So the in-center is the center of the triangle's inscribed in center. Remember, circumcenter, circumscribed. So in-center, inscribed circle. A circle is inscribed in a polygon if it touches every side of that polygon once. All right, so it has to do exactly 1 point. And look where that center is. And the cool thing is, if I was to do the angle bisectors, you would see right away that every one of them, look how when I connect it. Isn't that cool? Oops, that should be 2 marks each. Do 3 here. 2, 1, 2, 3. It always will go in the center. So that's where it gets its name. So inscribed is inside, circumscribed is on the outside. So that's where we get those. But here's going to be the rule that we have to apply. So let's apply a few examples on the other side.